Let's wrap up your notes on 11.3, limits and continuity. We left off looking at this piecewise defined function. We could see that we needed to check for continuity at 0 and at 1. In our notes, we looked at 0, we met all three conditions, and we could say the function f was continuous at 0. So now let's go ahead and check for continuity at 1. The first condition that I have to meet is f of a defined? So my a value is 1. So we have f of 1, which means x is 1. Now, if I look at all my intervals, 1 falls right in here. So that means I'm going to use the second line of my piecewise defined function, which is 2. It is a constant. And because 2 is defined, we can say f of 1 is defined, which means my first condition for continuity has been met. Let's look at the second condition. Second condition, does the limit of f of x as x approaches 1 exist? To check for that, we're going to need to look at the left-hand limit and the right-hand limit. So my left-hand limit, the limit as x approaches 1 from the left. So if I'm coming at 1 from the left, that means my x values have to be less than 1, which puts us again right in this interval. I'm going to use that second line again. And if you remember your properties of limits, the limit of a constant is the constant, so my limit here is 2. Let's take a look at the limit from the right-hand side. As x approaches 1 from the right. So if I'm coming at 1 from the right, that means my x values have to be greater than 1. And that is this interval right here. I'm going to use the third line, x squared plus 2. This is a polynomial, so apply your properties of limits. I can just plug my a value in for x, and I'm going to get 1 squared plus 2, which equals 3. Now notice my left-hand limit was 2. My right-hand limit is 3. My limits do not equal each other. So therefore, the limit as x approaches 1 of f of x does not exist. So I don't need to go ahead and check condition 3. It has already failed. We're going to say f is discontinuous at